Okay, so last time we saw the physical significance of these delta U, delta H, delta A, delta G, right? And what we realized last time was that no matter what goes down, whether it's U or G or H or A or anything, the basic reason behind a spontaneous change is always an increase in the entropy of the universe, right? And today I am going to formalize that thing. So today's lecture will be a lot more mathematical than it has been till now. Bear with me, but I'm sure you like maths more than chemistry. Oh, okay, thank you. So let's start from the Clausius inequality, or rather I would use the equality this time. When do we use the equality? When it's a reversible process, when things are in equilibrium, right? So my first law, I could write like this. And if I use the Clausius inequality, then dq reversible is nothing but TdS. And for the reversible work, let me write over there, only expansion is what I am looking at for the moment. In another couple of lectures, we'll include the non-expansion works also. Minus PdV. Yes? That's reversible. Only expansion work. Right? Now, although the way I've written this, it seems this is true only for a reversible process. No. du, internal energy is a Sage function. So the change in internal energy will not matter on how these processes are carried out. How I gain that heat or lose that heat, how I do that work, or the work is done, it does not depend on the path. Right? The total, the sum of it. So, although for the derivation I have written it like this, but this is going to be true always. But if you think of, an expansion work, then dW reversible is the maximum amount of work that you can get. If I have, this is also equal to incidentally dQ plus dW. So if I have dW in an irreversible fashion, then of course the amount of heat that will be taken up by the system would be also less. Yes? So the total would continue to be the same. So this is true for all processes. Okay. So if this is the case, what I see is that instead of using V, volume and temperature for variables of U, I could also use entropy and volume. So let me try to use this U, entropy, volume, and then I could write the change du as change in U with respect to volume. Please do not get confused between the U and the V's. Sometimes that sharpness might be missing. dV plus del U by del S V ds. Now, let me also at the same time do something. It's an important equation. It's known as one of the fundamental equations of thermodynamics. There are 4 of these, and I'll write each of them and color them so that you have a handy reference for later use. Now, if I compare these 2 equations, the one in green, and let me make another color over here. and the one in blue. What do I get out of it? I see that the change of internal energy with volume at constant entropy defines temperature. That's the essence of the law of thermodynamics. Which one? Huh? Not zeroth law. Entropy does not enter zeroth law. The third law. Third law is the one that goes all the way down to 0 Kelvin. Yeah. So, what I get from there is that del U by del V at constant entropy is temperature, and the other one that I get is del U by. I wrote the other way, huh? It's. Oops. Let me see if I can do a Control Z. Is minus P and del U by del S. Yeah, it should have been. And that's why I was saying that it's entropy, but I'm writing volume. Okay. So you get these two. And you remember how to check if a function is a state function or not. Double differential, right? So if I do this double differential, what I get out of this double differential? So the first term I have to differentiate with respect to entropy. Yes? Does it point out? Yeah. So this first term I have to differentiate with respect to entropy and equate it to the second term after differentiating it with respect to volume. Volume, right. So if I differentiate the first term with respect to entropy, that is minus of dP by ds at constant volume, and equate it with the second term dt dV at constant entropy. Yes? Any doubts? Yes? The no's are fine. The yes we have to worry about. No? I said yes or no again. That's good. Which one? Which part? You didn't understand up to here? This is okay? Now, if you have to ensure that a function is a state function, I have shown you only one technique till now. What was that? The double differential. So the double differential, if I differentiate on this fellow with respect to entropy, that is as good as differentiating this with respect to entropy. So dP by ds at constant volume. Nah. Sorry? That's what we do for the double differential. The first time you do it, you hold the entropy constant. The second time you do it, you hold the volume constant. So either you take one part, you take the perpendicular part, you hold one of those constants, right? So that's how I get this, and the same logic I get the right hand side. Still, if any doubt, because you will be using a lot of things of this kind, yeah. The double differential method is very, very straightforward. The definition of the state function. It says it does not matter what path I follow. Now, although what I am going to tell you now may not be exactly what I want to say, but